We'd just like to start by acknowledging the sacred land on which the University of Toronto operates. It has been a site of human activity for 15,000 years. This land is a territory of the Huron-Wendat and Chin First Nations, the Seneca, and most recently the Mississaugas of the Credit River. The territory was the subject of the Indigenous One's Wampum Belt Covenant, an agreement between the Iroquois Confederacy and Confederacy of the Ojibwe and allied nations to peaceably share and care for the resources around the Great Lakes. Today, the meeting place of Toronto is still the home to many Indigenous people from across Turtle Island, and we are grateful to have the opportunity to work in the community on this territory. So thank you for coming out to tonight's AstroTour. I'm Elisa Obertus, and I'm one of the co-directors for AstroTours. And if this is your first time coming out, AstroTours is a mostly monthly event run by the graduate students here at the University of Toronto in astronomy and astrophysics. And this is entirely run and organized by the graduate students. And so when you came in, we handed out some feedback forms. And after the talk, if you don't have your own pen or pencil, we'll have some available for you to fill them out, because we really value the feedback you give us to try and improve and keep on improving our monthly events. So tonight we have a fantastic talk about supermassive black holes by Dr. Rachael Alexandroff.
No, it's still weird that it's doctor.
Very excited. After the talk, we have planetarium shows, and we still have some tickets available, I believe, for the 10:50 show. Last time I looked, there was one left for 10:30. But so afterwards, if there are any tickets available, I'll make an announcement at the end of the talk. We have, hopefully observing, the forecast is a little mixed on whether or not we'll have clear skies, but hopefully it'll be at least partially clear. We can take a look at Jupiter and some other great things that'll be up tonight. And we also have some more activities, so I encourage you to stick around after the talk. And we also have refreshments upstairs if free food is enough of an incentive. So Dr. Alexandroff, giving her talk tonight, she studies supermassive black holes at the hearts of galaxies that we observe all across the universe, and she studies these to investigate how they interact with the galaxies in which they reside and how they shape and affect them. So you're originally from Toronto, right?
I am.
So she's originally from Toronto, but she did her undergraduate degree at Princeton, and she graduated with her PhD in 2017 from Johns Hopkins. And now she's back in Toronto, able to enjoy pretty much mandatory as an Ontarian canoeing. Just the right season for it to get started. So with that, let's welcome Dr. Alexandroff.
All right. Can everyone hear me all right?
Yeah.
Great. Thank you. Oh. Okay, now we're really ready. Thank you all so much for being here tonight. Now that the polls are closed, we can get on to the important topic of supermassive black holes. I am so honored to be here to talk to you all about one of my absolutely favorite subjects. I've been studying supermassive black holes for almost a decade now, and I think they're just the coolest, and I'm really excited to tell you about them. So one of the things that I think is super interesting about black holes in general is that though they were sort of first became an inevitability because of Einstein's theory of general relativity, Einstein himself actually was fairly convinced that black holes couldn't actually exist. That they were cool in theory, but you'd never actually find one out in outer space because they just didn't make any sense. So these enigmatic objects have been the study of both theorists and observers for the past 50 or 60 years, but there's still so many things that we don't understand about them. So today I'm going to tell you about some of the things we do know about black holes and supermassive black holes, but also some of the things that I like to think about that are open questions that seem really basic, but that are things that we still don't know about supermassive black holes. So to understand what a supermassive black hole is, first we have to talk about what a black hole is, and then what makes a black hole supermassive. So what is a black hole? The easiest definition to think of is that a black hole is an object that is so dense that not even light can escape it. So our little photon, our photon of light is trying to escape the black hole, but it can't. And what does that mean? Well, the escape velocity is a property that tells you about how fast you would have to go to escape the gravitational pull of an object back towards it. So when you think of a rocket blasting off from the Earth, for example, some of you may have watched the Falcon Heavy launch that happened, that SpaceX did a couple of months ago now, which was super cool. But they needed a rocket because they had to be going fast enough to escape the Earth's pull back towards itself. So you needed to reach a critical velocity. In the case of the Earth, it's 11 kilometers per second to escape the pull of the Earth's gravity back towards you. And how fast you have to go depends on how massive the object is that you're trying to escape, but also how densely you're able to pack all of that mass. So the escape velocity on the Earth is 11 kilometers per second. But if you go to Jupiter, Jupiter is much more massive than the Earth, and the escape velocity for Jupiter is 60 kilometers per second. So if you could stand on the surface of Jupiter, which we can't, but if you could, you would have to move at a speed of 60 kilometers per second to escape the pull of Jupiter's gravity back towards it. So that's how fast you would have to go to escape the pull of Jupiter. And we can keep going, but we can't keep going to infinity because eventually we reach the speed of light. So we now know that nothing can move faster than the speed of light. And so you can imagine an object that was so massive and so dense that the escape velocity you would require to escape the gravitational pull of this object would become greater than the speed of light. And as soon as you reach this limit, you've created a black hole. A black hole is an object that is so dense that that the escape velocity becomes greater than the speed of light, and therefore not even light can escape its gravitational pull. So I think this is the easiest way to think about a black hole. So I think I want to spend a little time clearing up some common misconceptions because there are many things that black holes are not. And in particular, black holes are not holes. You're not going into anything you're not going through something. You're not entering into a hole. Black holes themselves are not holes, but what they are, in fact, is very deep depressions in space-time. So every object that has mass, you, me, stars, and black holes, all bend space-time. And how much they do that depends on their mass. So stars, you can sort of see in this picture, bend space-time a little bit. And black holes, because they're so massive and so dense, bend space-time a whole lot. And I think the misconception kind of comes because sometimes this picture is drawn and there's like a hole at the end, but that's not what's happening. All that's happening is that this really dense object is causing a huge curvature in space-time. But it's the same thing that's happening for a star or any other massive object, just at a much larger scale. The other thing, I think maybe we can do that. Yes. So the other thing to think about is that some people think of black holes or describe black holes as vacuum cleaners that sort of suck up everything in the vicinity. And that's also not quite correct because you can orbit, as you can sort of see here, this is a little diagram of the Earth orbiting the sun, and you can do the same thing for a black hole. You can orbit around a black hole as long as you're far enough from the gravitational influence that you don't end up spiraling in. You can still orbit around a black hole. Just like we orbit around the sun, stars can also orbit around black holes, or any kind of object, in theory, can orbit around a black hole. So they're not exactly these cosmic vacuum cleaners that suck up everything. They can swallow material, but it's not a foregone conclusion that's guaranteed to happen. So these are important things, I think, to keep in mind about black holes. And I always like to mention this because I think it's kind of a fun Canadian fact, but one of the first black holes to ever be properly confirmed was actually confirmed by a Canadian astronomer, Dr. Tom Bolton, who worked at the David Dunlap Observatory, which some of you may have been to. It's just up north of Toronto. And this black hole was found because it was orbiting, it was in a binary star, so it was a black hole that was orbiting a star. And what was happening is that the material from the star was being sucked off into orbit around the black hole, and this very energetic process produces X-rays that can be seen here on Earth. So this I think is kind of neat because it's a little sort of Canadian connection. So black holes have been studied for a very long time, but in particular, they have been studied by Canadians for a very long time. So where do black holes come from? So for these black holes that I've started to tell you about, these black holes that weigh about the mass of the sun or a couple times more, they usually come from the explosions of supernova. So what you saw there was a massive star that collapsed under its own gravity and caused a supernova explosion. And the remnant from that supernova explosion is showing up here. So every once in a while, within our galaxy or within nearby galaxies, we see stars explode, but usually what we see is what's left over after a star explodes, which is the supernova remnant. And what you can't see, however, is that for very massive stars, when they collapse under their own gravity and go supernova, the remnant that's left over at the center could actually be a black hole of several to tens of solar masses. So these small, in black hole terms, these small black holes are usually formed by the collapse of massive stars. So now that we understand what a black hole is, the next question becomes, what makes a black hole supermassive? So I've talked about stars that weigh about the mass of the sun, a couple times the mass of the sun, and you might think, that seems pretty massive to me here on Earth, but that's nothing compared to the mass of a supermassive black hole. So supermassive black holes sit in the centers of galaxies, and they typically weigh about 1 million to 1 billion solar masses. So we're talking sort of a whole different category of objects here. So a supermassive black hole lies at the center of almost every galaxy, and that includes our own Milky Way. So the Milky Way hosts a supermassive black hole that weighs about 2.5 million times the mass of the sun. So that's actually kind of small on supermassive black hole scales, but overall is pretty impressive. So just how big is a supermassive black hole? So one of the things I talked about earlier is that a black hole is a really dense object. We have packed a lot of stuff into a very small space. And that's how you create this gravitational pull that is so strong that not even light can escape the pull of a black hole. So though the supermassive black hole at the center of our galaxy weighs approximately 2.5 million times the mass of the sun, we've packed all of that stuff into approximately 1,000 times, just 1,000 times the volume of the sun. So there's a huge amount of stuff here that we're packing into a really small space. And any object, obviously, or any object can become, if you compressed it enough, could become a black hole. It would just have to be extremely dense. So for example, if you took the Earth and you wanted to compress it so much that it would become a black hole, you would end up with an object that's about 0.7 inches. So approximately, we did this like roughly the size of like your thumb. So you would have to take the entire mass of the Earth and compactify it into this tiny, tiny little region to produce an Earth mass black hole. So in comparison, if you took a human and you wanted to compress a human so much that you could create a human mass black hole, you would have to compress a human down to such a tiny volume, a fraction of a volume of a proton, that it's a size that it's so small I can't even come up with a good analogy to describe it. These things are extremely, extremely dense. So the black hole at the center of our own galaxy, the center of the Milky Way, is extremely massive and seems to be really large. But on the scale of the galaxy, it's actually quite small. So the ratio between the size of the supermassive black hole at the center of our galaxy and our galaxy itself is approximately the same as the ratio between the size of a penny and the size of our sun. So though these objects are really, really massive, and they seem really big to us, on galaxy scales, they're actually quite tiny. And this will come back later into some of the things I want to tell you about in my own work, which is whether an object that seems, can seem quite massive, but in reality is quite small, can have any effect on the galaxy that it's sitting in, because it's taking up only a small, small fraction of the size of the galaxy. So we've talked about these objects, and the very first thing we talked about when it came to black holes is that black holes are objects that are so dense that not even light can escape them. That's great, but if that's true, how do we know that they exist? How can we go about finding an object that doesn't emit any kind of light? And this is one of the reasons I think that it took so long to verify that black holes were real, is because people had to figure out ways to find them when you couldn't see them. So it's like, if you think about, if you looked outside one day and you saw all of the trees in your backyard were bent over in a particular direction, you would know that the wind was blowing in that direction, even though you can't see the wind. And that's the same thing that we're trying to do here. We have to find out ways to prove that black holes exist, even though we can't actually see them. And the way we do it is exactly the same. We look at the effect that the black hole has on the objects around it. So even though it itself doesn't emit light of any kind, we can see how it affects the objects around it. And this is what can tell us that a black hole is sitting somewhere, even if we can't see it. So this is one of my favorite videos. So we can do this in a number of different ways, but one of the ways we determine that supermassive black holes exist is by tracking the orbits of stars around them. And you can only do this for objects that are very close by, and really for only two supermassive black holes, one of which is the black hole at the center of our galaxy. So this is an animation of real data. Astronomers since the 1990s have been tracking the orbits of stars around the supermassive black hole at the center of our galaxy. And they've been doing it for so long now that some of the smallest, that you can determine really well the orbits of some of these stars, especially the ones that are closest to the supermassive black hole. And this is what allows us to determine that there's a supermassive black hole there, because you know how fast these stars are orbiting and where they're orbiting, and that tells you how massive the object is that they're orbiting around. And so we can say with great confidence that these stars have to be orbiting around an object that is so massive, that's packed into such a small space, that the only possible explanation is that they're orbiting around a supermassive black hole. So even though we can't see the supermassive black hole, we're watching its gravitational effect on the stars that are orbiting around it, and that's what's providing us with the evidence that there's a supermassive black hole there. So the other way that we can detect the presence of supermassive black holes are by studying these objects called active galactic nuclei, or AGN. This is the only acronym I'm going to use in this entire talk, I promise. But these objects are sort of exactly what they sound like, which is that they're galactic nuclei, or in this case, supermassive black holes that are active. So they're interacting with their environment around them, and we can see the signature of that. So though the black hole itself is not emitting, there's a lot of stuff around the black hole that is, and that's what we're going to be able to study. So this picture here is a fairly typical galaxy. What you're actually seeing, so the white sort of light circular part, that itself is the galaxy. So these are hundreds of thousands of millions of stars that you're seeing here, and they're so faint and far away that it's all smeared together into this sort of white circle. And then actually what you're seeing here is a lane of dust lying between us and the galaxy. So the dark spot is just dust sitting in between the light from the stars and us at the edge of the galaxy. So this looks like a typical galaxy when you look at it with really sensitive eyes that are staring just like ours. So if you had, extremely sensitive eyes, you would be able to see something like this just with the light that our eyes can see. But what's interesting is that if you peer with a telescope that doesn't look in the wavelengths that our eyes are used to looking at, but instead looks in the radio, so like you would use for an FM or an AM radio around you, you actually see something that looks like this. And this looks totally different, which is kind of crazy. And what you're actually seeing here is the interaction of energetic particles coming from material around the supermassive black hole with the environment around the galaxy. So there's a huge amount of energetic particles being released by the supermassive black hole or by the material around the supermassive black hole. And those are interacting with material on galactic scales and producing this emission. So if you put this whole picture together, you can see that though the black hole is really tiny on the scale of the host galaxy, it's actually producing emission that is about the same size as the host galaxy. So this signature is really bright and really powerful, and we're able to see it and study it, and that's what tells us that a black hole is there in cases in which it's actively producing this kind of energy. So how does this happen? How does a supermassive black hole emit these kinds of energies? So what happens is that there's material that's orbiting around the supermassive black hole, gas and dust. And this can be pulled into orbit around the supermassive black hole and then eaten up or destroyed if it gets close enough to the supermassive black hole. So it's just torn apart by the very high gravitational forces in or near the supermassive black hole. And this process is not like a vacuum, as I described earlier, and it's not material falling in, but it's actually material that's swirling around the supermassive black hole. So it acts kind of like, a supermassive black hole acts like the drain in your bathtub, and the gas and dust and stars that are orbiting the supermassive black hole are like the water that's spiraling into the drain of your bathtub. And this kind of action actually produces a huge amount of energy, because you can imagine there's a lot of friction between the particles, there's a lot of particles interacting, and this process, as this material spirals in to the supermassive black hole, is extremely energetic. It's going to release a lot of energy, and it's this energy signature that we're seeing on galaxy scales when we view these active galactic nuclei. So this isn't happening in every supermassive black hole, in every galaxy. Our galaxy, for example, does not have a supermassive black hole that's an active galactic nuclei. We got really excited 5 years ago when we thought it was going to swallow like one tiny cloud of gas. And it didn't end up happening. It was very disappointing. But this doesn't happen for every object. It happens for, we think, approximately, at any given time, approximately 10% of galaxies will have supermassive black holes that are actively accreting matter, which means that that something is driving all of this stuff toward close enough that it's able to spiral into the black hole and produce this huge energy signature. So what we can do then is take these active galactic nuclei and we can use them as tracers for black holes. So the majority of supermassive black holes can't be seen. We can only trace the orbits of stars around the 2 or 3 supermassive black holes that are the nearest to us in the universe. But these active galactic nuclei are extremely energetic, and therefore we can see them all across the universe. We can look at AGN that were active, millions to billions of years ago, and they can tell us about what supermassive black holes were doing at these times. So these objects in themselves are extremely interesting, but they're also powerful as tracers for supermassive black holes across the age of the universe. So what I think is really awesome is that there is still so much we don't understand about supermassive black holes. And in particular, there are really basic questions about supermassive black holes that we still don't understand. For example, how do you build a supermassive black hole? How do you get something so large into your galaxies? We aren't 100% sure how this happens. And sort of as I alluded to earlier in this talk, what I study, which is how do supermassive black holes affect the host galaxies in which they live. We've seen now that active galactic nuclei are these extremely energetic objects. And so do they have any effect on the host galaxies that they're sitting in? We're still not 100% sure in what way they affect their host galaxies, even though we've been studying black holes since the 60s and 70s. So I think that these questions, it's crazy to me that these fundamental questions are still sort of open, but really interesting to think about the answers to these questions and how we would go about solving them. So the first thing I want to talk about is how do you go about building a supermassive black hole? So I mentioned earlier that we know that sort of solar mass black holes of a couple times larger than the mass of the sun form when massive stars go supernova, when they explode and the remnants collapse to form a black hole. But how do you build a supermassive black hole that's 1 million to 1 billion times the mass of the sun? And in particular, we've now seen active galactic nuclei that existed only 700 million years after the Big Bang. And we're able to do this because the speed of light is constant, and therefore, the farther away we're looking in space, we're actually looking farther back in time, because the light coming from these objects has taken a long time to reach us. So the more sensitive our observations, or the farther away we're able to look, actually the farther back in time we're also looking. And so our new instruments have allowed us to discover active galactic nuclei that were in existence only 700 million years after the Big Bang. So now we are starting to run into a problem where we have to build an extremely massive object, and we have to do it very quickly in terms of the age of the universe. So where do these supermassive black holes come from? And we actually still have two competing theories, because doing these observations is very difficult because these objects are so far away. So our first theory is that massive, very massive stars collapse to form the seeds of what will grow into supermassive black holes. So the very first stars at the beginning of the universe were thought to be more massive than stars that we see today. And so these stars might collapse to form what we call seed supermassive black holes that would have had masses of about 100 to maybe 1,000 times the mass of the sun. And then these seeds would go on to merge relatively quickly to form the supermassive black holes that we see today that weigh about 1 million to 1 billion times the mass of the sun. So this is one theory, but there's actually a competing theory that you don't even form stars at all, but instead you take massive gas clouds in the early universe and they collapse under their own gravity directly to form seed black holes that instead weigh about 10,000 to 100,000 times the mass of the sun. And it's this difference that we're interested in, whether the seeds of these black holes were about 100 solar masses or 10,000 solar masses. And so then these seeds themselves will go on to merge and form today's supermassive black holes. So how do you distinguish between these two scenarios? In order to do so, this is one of the science cases for the James Webb Space Telescope that's been built over the last number of years and is now set to launch in summer 2020. I used to be able to say it was set to launch in fall of 2018, but that's not true anymore. But it's going to happen. It's going to be great. James Webb is set to launch in the summer of 2020, and it's going to sit at L2, which is this point that's actually farther away from the sun than the Earth by a decent amount, by 1,500,000 kilometers. And the reason we're putting it there is actually because we need to put a sunshade in between the telescope and the sun at all times, and this orbit allows us to do so. So these instruments on this telescope are so sensitive that light from the sun would totally overwhelm them, and so you have to keep a sunshade in between the telescope and the sun at all times. So I have to show this video because it's totally awesome. This is the James Webb Space Telescope. This is an animation of what it's going to do as it's flying from the Earth out to L2. So it's going to come sort of compactified up in a rocket, and then it's going to have to expand in order to be operational. So this is both exciting and for astronomers extremely terrifying. What you can see here is the sunshade opening up. So this is what's going to protect the telescope from the sun. That's popping up. And then the mirror itself is actually not one big mirror like you might think of for most telescopes or some of the ones that you might use this evening, weather permitting. But it's actually made up of a number of different segments that can be folded up to fit inside the rocket. And then these segments, in a second, are going to unfold, and we'll be finally ready with the telescope to do some observing. So there you go. So all of those steps have to happen successfully for us to be able to use this telescope, which is why astronomers are slightly terrified. But this is going to be one of the most sensitive telescopes that astronomers have ever built. And then, as a result, it's going to allow us to peer very far away in space and very far back in time. So this instrument is going to be able to allow us to observe some of the first galaxies, but not only some of the first galaxies, also some of the first active galactic nuclei. And so we're hoping that by doing this, we'll be able to distinguish between the two scenarios I presented to you earlier and understand where it is that supermassive black holes come from. So this is one of the questions that I'm eagerly awaiting the James Webb Space Telescope to help us resolve. So if you come back and hear someone give a talk about this in 5 or so years, hopefully someone will have an answer for the question that I posed to you today. And the other thing that I like to think about, and in particular, this is sort of the area of research that I work on, so I wanted to tell you a bit about it, was how supermassive black holes affect the host galaxies in which they live. And in particular, do active galactic nuclei, these extremely energetic versions of supermassive black holes, affect their host galaxies? And we think the answer is yes. And the reason we think that supermassive black holes affect their host galaxy is that we've built up a lot of data to show us that there's a strong correlation between the mass of a supermassive black hole and the mass of the host galaxy that it's sitting in. And this is a relatively tight correlation that exists for supermassive black holes on a wide variety of scales, from about 100,000 solar masses up to 1 billion solar masses. It's very consistent. And so this gives us a hint that something's going on, that some interaction, likely between the black hole and its host galaxy, is driving this relationship, is producing some kind of relationship between the mass of the galaxy and the mass of the supermassive black hole. And so we need these objects to interact to produce this kind of relationship that astronomers have observed. So how might this happen? Ooh, unfortunately this always goes green. No? It'll stop being green in a little while. I don't know why that happens. But anyway, the theory of what's going on is actually that this relationship is driven by the merger of two galaxies. There we go. So these two galaxies, this is a simulation, these two galaxies have been driven onto a path in which they're going to merge. And you can see here all these particles are gas particles, and the color shows the temperature, or how hot they are. So as these two galaxies merge, just due to gravity, all of this gas and dust is getting kicked up and sort of pushed around into unstable orbits. And one of the things that does, all this gas and dust could end up being funneled towards the central supermassive black hole. And I'm going to play this again, sort of show it to you. Ignore the green. But so as these two galaxies start to merge, you're going to kick up a lot of gas and dust, and then you're going to funnel it towards the central supermassive black hole. And that action is going to start this bathtub process by which all this material is going to be funneling towards the supermassive black hole, and that's going to release a lot of energy. And that energy is then going to interact with the remaining material in the galaxy, and you can sort of see that happen in just a second. And what it's going to do is it's going to push on all of the remaining material in the galaxy and blow it out of the galaxy. So you can actually see the supermassive black hole turn on right there, and that process is going to push the remaining gas out of the galaxy and leave us with this remnant that in which most of the gas has been removed. And the important thing to remember about this is that we need gas in galaxies to form stars. Stars are formed by the collapse of gas clouds. And so if you've removed the gas from the galaxy, if the energetic supermassive black hole has removed the gas from the galaxy, we're going to stop forming stars. So we think that supermassive black holes that are actively accreting, that are active galactic nuclei, can actually shut off star formation in their host galaxies by pushing the material for star formation, this gas, out of the galaxy. And this is one more video I just wanted to show you. So we can't actually observe this happening for any particular object because we're only looking at the snapshots of a particular object at a particular point in time. Any evolution that we would see would happen on scales that are way too large for a single human to study. So instead, what we do is we make observations and then simulations, and we compare those to observations. So what I'm showing you here is a video, another video of two galaxies merging. This one doesn't actually have supermassive black holes in it because they're very complicated to add in. But what you can see here, I'm going to play it again, is that this simulation is going on. They're merging two galaxies, and every once in a while they're stopping, and they're showing you a real observation of two galaxies in a merger that we've seen with a telescope from Earth. So we take these simulations, we compare them to our observations, and then we use them to inform each other, to tell us about what the simulations can tell us about the observations, and then what the observations mean in terms of how the galaxies are evolving. Because we can't see one galaxy pair go through a merger. That process takes, tens of millions of years. Instead, we can observe multiple galaxies at different stages in their own merger process and use those together with simulations to create a picture of how a galaxy merger works. And that's the kind of work that astronomers do when we study galaxy mergers. So I think this is cool because each of these little stop motion times is a different actual picture of a galaxy merger. And they look remarkably similar to the simulation that's going on here. And so this gives us a good indication that the simulation is doing its job. It's actually producing realistic simulations of a galaxy merger. But to reiterate this picture, what we're interested in is how the active galactic nuclei, so this supermassive black hole that's producing a lot of energy, is affecting its host galaxy. And in particular, if these energetic particles are removing gas from the galaxy, this would cause a shutoff in star formation. So in my little diagram, there's no star formation happening in the area near the active galactic nuclei because it's been energetic enough to remove the material for star formation, the gas, from the host galaxy. And it's possible there are still knots of star formation happening elsewhere in the galaxy. So there could still be stars forming in the galaxy in regions that haven't been reached by this energetic supermassive black hole. And so this tells us that we want to understand a couple of things about the galaxy. We want to be able to take a picture of the galaxy because we want to know where is star formation occurring, where is the actively accreting supermassive black hole, are those things in the same place or are they in different places? And we can tell that by taking an image. But we also want to know something else. We want to know how the material is moving throughout the galaxy. We want to know at what speed all these particles are going. And we can actually do that by using something called the Doppler effect. So a normal galaxy has some particles, and all of these particles are emitting, has some amount of light that we see with our eyes, and it looks all across the optical spectrum. So we'll see light that our eyes can see, but only more sensitive. But if that star or particle is moving towards you, that causes a blue shift or a shift in the light that we can see as the wavelength gets sort of scrunched up. And if the star or the particle is moving away from you, that causes a red shift because we've stretched out the wavelengths of the light that we're looking at. And this can tell you about the velocity or the speed with which the object is moving towards or away from you. So we not only want to take an image of where all the stuff is in the galaxy, but we also want to know the speed at which it's moving. And we can do that by looking at the wavelengths of the light, by how much they've been stretched or compressed. And so we want two different pieces of information. We not only want this picture, but we want to know how the stuff is moving in this picture. And that requires a specific kind of instrument that is called an integral field unit spectrograph. And this object allows us to get both of these pieces of information together. We're not only getting an image, but we're getting an image at every different wavelength, which is telling us about how the particles in this galaxy are moving. So we take an image of our object, but we also get movement of the gas across the object using this instrument. So this is an extremely powerful technique. And integral field unit spectrographs are relatively new, but they're becoming increasingly common. So for example, the James Webb Space Telescope that we talked about earlier is going to have 2 different integral field unit spectrographs on it to allow us to get this picture of moving gas across a galaxy. WFIRST, which is another mission that astronomers are talking about that would launch in the early 2020s, also might have an integral field unit spectrograph. And on the ground, large surveys like MANGA and other surveys are using these instruments to look at how gas moves throughout galaxies, with the idea of trying to understand that picture I showed you of where stars form in a galaxy with an active galactic nuclei, and how this energetic emission being released by the supermassive black hole, how the energetic material is interacting with the surrounding gas and causing it to move around. So black holes are everywhere, and in particular, supermassive black holes sit in the center of almost every galaxy. And we study them often by looking at these objects called active galactic nuclei, which are energetic supermassive black holes. And they're allowing us to trace supermassive black holes all the way out now to the very edges of the universe. But there's still so much we don't know about supermassive black holes, like where did they come from and what effect do they have on their host galaxies. But these new telescopes we're building, for example, the James Webb Space Telescope, will hopefully, in the next couple of years, help us to answer some of these really fundamental questions about supermassive black holes. So that's everything I wanted to tell you about this evening. But if you have any questions, I can take them now. Thanks so much.
Wonderful. Thank you very much, Dr. Alexandroff. So I'll try to see if we can get a mix of questions from across the room. So
Sure, yeah. Do you want me to call on people, or do you want?
You can call people if you want, and just repeat the question.
Yeah. All right. Yeah, right at the front to start.
When you showed the image of the galaxy and the radio emission,
Yeah.
it looked like the emission was coming out into jets. Why is that?
All right, so the question is, the radio emission sort of looked like it was coming out not in a sort of circle, but in these two jets. And why is that? And this is actually a really interesting question. So we do think that some subset of active galactic nuclei show these radio jets. It's not every galaxy. It's about 10% of active galactic nuclei show radio jets. And the actual mechanism for jet launching is not totally understood. But basically you see, or how you actually start these is not well understood, but what's happening is that you're spiraling magnetic fields up off a plane that's so you have the black hole, you have this accretion disk, all this material that's being sort of funneled into the black hole like the bathtub, and then perpendicular to that, you have these, you're twisting the magnetic fields, and then particles, energetic particles are following along those magnetic field lines, and that's what's producing the radio jets. Yep.
So I've read somewhere that black holes do evaporate. Is that how they evaporate?
So black hole evaporation, so the question is, do black holes evaporate, and is that how? Black hole evaporation is a sort of a different thing. So all the stuff that I've talked about is how material around the black hole is interacting with stuff that's going on. So it's not actually the black hole that's doing any changing, other than that it's eating material and it's growing. We do theoretically think that black holes could evaporate. But sorry, I'm like really, my throat is sore from talking so much. But it would be like immeasurably slowly. It would have, like, especially for a black hole of this size. And that's caused by, like, in theory, by Hawking radiation. So it's a different kind of mechanism. Yeah. At the very front again? Yeah.
Background microwave radiation that's going on, is that the same as a light particle?
Yeah, so the cosmic microwave background is a specific kind of light particle, yeah.
And so this vacuum cleaner is cleaning that up.
So supermassive black holes don't interact very much with the cosmic microwave background. There is one measurable effect that you can get, but in general, those energetic particles are fairly low energy and are not interacting with the galaxy until we observe it here. There are some small effects, but main effect is very little.
Okay.
Yeah. in the middle. There's sort of two of you. We can do one and then the other.
So I guess two really quick ones. First one is, if supermassive black holes form like the early universe, and they're in the center of pretty much every galaxy, does that mean that galaxies form around like the supermassive black holes are the reason that galaxies exist? And the second one is, are there any galaxies that don't have a supermassive black hole?
All right, so two-part question. One, are supermassive black holes the reason that galaxies exist? And two, are there galaxies without supermassive black holes? So for the first, to answer your first question, I think it's more a symbiosis. So the materials get, basically what happens in the early universe is that there are areas that are more dense and areas that are less dense, and material is flowing towards the more dense areas. So you're naturally forming both supermassive black holes and galaxies at the center of these sort of more dense regions. And yes, you will notice that I was really careful all the time to be like almost every galaxy, because there are some galaxies that don't host supermassive black holes, and those are mostly the least massive galaxies. So smaller galaxies called dwarf galaxies don't always have supermassive black holes. Though we used to think none of them did, and relatively recently we started discovering that some of them do. So this is actually a question that's evolving. But there are definitely dwarf galaxies, smaller galaxies that don't have any supermassive black hole at all. And then next door, because
okay, so,
I couldn't pick.
You mentioned when the black holes kept eating matter, it's kept pushing out all the gases. I guess that's probably radiation pressure generated.
Yeah.
If that's enough radiation pressure to push out enough gas to disrupt star formation, now here's the question: if something were to happen in our own Milky Way of such magnitude, what would happen to us?
Yeah, so the question is, like, if the active galactic nuclei at the center of our galaxy turned on, would that be bad? So, yeah, it's funny. I've actually read, like one or two papers where people have done sort of calculations like this, where they're like, would this be a bad thing? To which the answer is like, yes. Would not be awesome. We're not in any danger of this happening, so I wouldn't like worry about it on a like day-to-day level. But it would not be great. You would have more problems too from, so like these are very energetic events, so there's huge amounts of energy all across the electromagnetic spectrum that are released by an active galactic nuclei, and like that would also be pretty bad for us. So all around, not great. We're like far enough out from the center of the Milky Way that like maybe we'd get off okay, but
It's not good for living things that are features or things that are alive.
no, not great for life in general. The back over there? Yeah, that's you.
So, can you use like gravitational lensing to detect black holes, or that's not?
So the question is, can you use gravitational lensing to detect black holes? And yeah, you can. And so there are, gravitational lensing is basically another prediction from Einstein's theory of general relativity. If you think of that image that I showed you at the beginning, where large masses are able to curve space-time, that actually can curve the path of light as it's traveling towards us. So if we had, for example, like a galaxy and it was emitting light, and there happened to be a supermassive black hole in between us and that galaxy, the light coming from that galaxy would be bent by the supermassive black hole, either towards or away from our line of sight, and we would be able to detect that. That's gravitational lensing, and we would be able to detect that. People are trying to do that to look for like intermediate mass black holes in our own galaxy, and other kinds of studies like that. Nothing successful so far as I recall, but it is something that people have thought about, absolutely. In the front?
What's my sound? You're saying,
Oh, no worries. If you remember, we'll come back.
Yeah, those bursts of energy, are they the same as the quasars?
Yeah, so the question is, what is this? Is this a quasar? How is this related to a quasar? To be very technical, though I didn't use the word, quasars are actually the objects I study. Quasars are just luminous active galactic nuclei. So they're the objects they're the very, because we like to name things, they're the very energetic active galactic nuclei are called quasars, and that just has to do with the fact that they were discovered somewhat differently, and so we gave them a different name, and then we realized they were the same.
So it's called pulsars?
Pulsars are, so the question is, what are pulsars? Pulsars are actually a totally separate thing. They both have a similar sounding name, quasar and pulsar, because they were both discovered in the radio, and I think that's what they make the R sound. I'm not totally sure, but they sound very similar, but they're actually quite different. Pulsars are rapidly rotating neutron stars. So in our galaxy, where the rapid rotation causes you to see these pulses as they're magnetic, as they have magnetic fields as well that beam stuff towards us. But they're a very different scale. So pulsars are neutron stars, so 1.4 solar masses. Quasars are a certain kind of active galactic nuclei. So these are supermassive black holes sitting at the centers of galaxies. But both discovered in the radio, so our names. Yep.
Just curious, what is one of your favorite phenomena or facts that you learned about supermassive black holes?
My favorite, sorry?
What's one of your favorite facts or phenomena that you learned about supermassive black holes?
One of my favorite facts about supermassive black holes. That's actually a hard question. Okay, I'll tell you a slightly different thing, which is something I'm also really excited about that I didn't get to talk about, which is that there's a group of telescopes called the Event Horizon Telescope that is trying to image what's called the event horizon of the supermassive black hole at the center of our galaxy. And that's basically, they want to look at right before the part where you get so dense that light can't escape, right on the other side of that. So the very, very edge of the black hole. They're going to try to image that using a network of telescopes, and they did. So it's very complicated because they have telescopes all over the world that all for taking data at the same time, and one of them is in Antarctica. So they took data last winter, but then they couldn't get it until relatively recently because you have to wait till you can come back to Antarctica to pick up the data. So they're just now starting to analyze the data from a year ago to try and image the event horizon of the supermassive black hole at the center of our galaxy. And I think it's going to be super cool and exciting. Everything about supermassive black holes is awesome. So,
Thank you.
No worries.
It might be a silly question, but
No.
when you were talking about the velocity needed to escape Earth's gravity,
Mm-hmm.
and then you talked about light escaping a black hole.
Yeah.
How do you know there's light in there?
Well, it's not even necessarily that you know that there's light in there. It's that any light that you can't, no light could possibly escape. So anything that's in there, and because there's mass, it has some mass, there's something in there, could never escape. So it's not so much that we know there's light sitting in the center, as anything that's sitting in there couldn't possibly escape. And we know that there is some mass in there because it has mass. Yeah?
That's bringing up the dark field, the dark matter, and dark energy. Could that black hole be more a function of that dark field?
So so the question is, how does this relate to dark matter and dark energy? Dark matter and dark energy are sort of two separate things, but there is an open possibility that some percentage of dark matter in our universe is black holes. Some people are more or less in support of this idea, but basically there's this huge percentage of the energy and matter budget of the universe that we don't understand. And that's what dark matter and dark energy is. And we have some constraints on the amount of dark matter that could be due to black holes, but there's some wiggle room. So it could be that some percentage of the dark matter in our universe is from black holes of, I think, between 30 and 100 solar masses, but we would know, and actually this relates to one of your previous questions, we would know if most of the dark matter was black holes bigger than that because we would see them with lensing, and we don't, so it can't be that. And so you can put constraints on it that way. But there is a chance, and people argued about this relatively recently. So it's still an open question that some percentage of dark matter could be coming from could be black holes that we can't see, and so that's why it's dark matter.
We'll just take 2 more questions. I know there's
Yeah. Oh, sorry. I'm so sorry. No, I'm just sorry I haven't called on you earlier. Anyway, yes.
I heard recently about something called a Planck star. It's like an opposing camp from the black hole people. Can you tell me more about it? I don't know. Apparently the math works with the Planck star, and then the black hole math doesn't work yet.
For dark matter candidates, you mean specifically, or?
Like, the question of whether black holes actually exist.
Oh.
In the singularity as it exists to them.
Cool. Okay, yeah, I have to say, I actually, so this question was about Planck stars. I actually don't keep up on like the latest theories about what else black holes could be, so I don't know anything about Planck stars, so I wish I could have a better answer for you. What I will say is that when we want to come up with an alternative theory to something like black holes or dark matter, it's a very high burden of proof where you have to match every existing observation and then make a prediction that's different from our current theory and then have that proved. So people, when they try to come up with, for example, like alternative theories of gravity to replace dark matter, have to be able to explain like everything we can explain with dark matter, plus make additional predictions that turn out to be true over what you would predict about dark matter. So I don't know anything about Planck stars, but I will say so far, everything we've predicted about black holes holds up and is consistent, but that's not necessarily to say that there couldn't at some point be some discovery that overturns that because it's inconsistent with black holes, but consistent with something else. And I try to keep an open mind about things like that.
So let's take one more question, but Dr. Alexandroff will still be available for a few more minutes after the talk if you have any questions that have yet to be answered.
I think in the middle there, yeah.
With thoughts on the dark matter in the galaxy, what kind of effect would you get if a mass of dark matter maybe entered an AGN?
All right, so the question is like, how would dark matter interact with an active galactic nuclei? So dark matter is still, so the things that we know about dark matter is that it only interacts by the gravitational force, but it still does interact via gravity. So it would be fairly similar to gas, to any other kind of material you can come up with, except for that some of the predictions would be different because certain forces that are at play would not be there. But other than that, it would interact the same way due to gravity that any other. So if a ball of gas falling into a supermassive black hole or a ball of dark matter would have a similar effect in terms of gravity. But you might not see any signature because there would be no energy. So dark matter is still just a kind of matter. It's not it's not negative matter. So it would interact in the same way any other kind of matter would. Yeah.
So let's thank Dr. Alexandroff for a